The Black-Scholes model is an option pricing model used to price various kinds of options. For example, it can be used to price equity options, currency options, commodity options, and bonds. The Black-Scholes model has two main components. First, it has a partial differential equation, of which there are many variations depending on what type of derivative we are pricing, that is used to describe the dynamics of the option price and of its different variables and parameters. Second, it has its individual solutions to the PDE, which allow to price the options themselves based on strike price and maturity and their particular payoff structures. An option is a financial contract about an underlying asset, which we can represent as a stochastic process. Here, S is the underlying asset's price, and dx is the source of randomness in the form of a Brownian motion. The mu s dt term is the deterministic time trend or the drift of the process. And this is the Black-Scholes PDE. V is the theoretical option price at time t for an option of maturity capital T. S is the underlying's price at time t. Sigma is the underlying's constant volatility. C is a continuous cash flow that the underlying may provide, which is, for example, for equities, it can be a dividend. For currencies, it can be the foreign interest rate. And for commodities, it can be the cost of carry. And R is the risk-free interest rate. From a sell-side perspective, when you set the price of a derivative you are selling, you don't want to give away free money. In other words, you don't want to give away arbitrage opportunities. Therefore, you will price the derivative in such a way that when you hedge away the random component, or risk, you get a return no greater than the risk-free rate. This risky component is dx, the Brownian motion of our underlying stochastic process ds. This risk-free derivative portfolio, which we will soon see how to construct, is therefore mathematically expressed as d pi, the change in our portfolio over time, equals r times pi times dt, the risk-free return on our portfolio. Now the question is, how do we build such a risk-free portfolio? The simple answer is that we must short an appropriate amount delta of the underlying asset. We will see how this works and how delta is calculated. This is called delta hedging. Let's derive the PDE. First, we start with our hedge portfolio, pi equals v minus delta s. We want the derivative, d pi equals dv minus delta ds. Notice that delta stays as is because it does not change within a time step dt. Now we apply Ito's lemma to v in order to get the explicit form of dv. References on Ito's lemma can be found in the video description. And now we delta hedge to get our risk-free portfolio. We find that in order to remove the ds terms from the previous equation, we need to set delta equals the partial derivative of v with respect to s. So we substitute delta back into the equation and the ds terms disappear. According to the no arbitrage principle we discussed earlier, this risk-free portfolio must change with time in a manner equivalent to the risk-free rate. Thus, d pi equals r pi dt. Substituting the d pi we obtained in the previous slide and the pi we started with, we get this formula. We can divide both sides by dt to get rid of them. And now by trivial rearrangement of this last formula, we obtain the Black-Scholes PDE, which completes this derivation. Solving this PDE is a boundary value problem with two boundary conditions on S because it's of second order, and one final condition on T. The final condition on T is the option payoff. For puts, the payoff is the maximum of k minus s or 0, where k is the strike price. For calls, the payoff is the max of s minus k, or 0. The boundary conditions for calls are 1. As s tends to infinity, v tends to s plus a contract premium. And 2. As s tends to 0, v tends to 0. For puts, these boundary conditions are as s tends to infinity, v tends to 0, and as s tends to 0, v tends to the discounted strike price. The process of solving the PDE is beyond the scope of this introductory lecture, so I will only give a few standard results. This is the European call option value formula. When the option is at the money forward, in other words, its price is close to the present value of its strike price, there is an approximation to the call value, and this is the formula for this approximation. This is the formula for the European put option. Because of the put-call parity principle, the approximation of the at-the-money forward formula for the put is the same as that of the call. Binary options are also called digital or all-or-nothing options because they return a payoff of 0 or of a fixed amount. Their payoff functions are, for the call binary option, v equals the Heaviside function of s minus k. The Heaviside function is a function which returns the predetermined given fixed amount when the argument is positive or 0 otherwise. And for the put option, v equals the Heaviside function of k minus s. And these are the binary call value equations for the call and put options. And finally, let's take a quick look at the assumptions behind the traditional Black-Scholes model. First, delta hedging must be done continuously. Second, the underlying follows a geometric Brownian motion, or log-normal random walk. Third, there are no discontinuous or variable dividends. Fourth, the risk-free rate is a known function of time. Fifth, there are no transaction costs, no taxes, no limits to trading. In other words, there is frictionless trading. 6, there are no arbitrage opportunities. And 7, the volatility of the underlying is a known function of time.